Welcome, everybody. This is a big crowd. I am very happy to be here. Thanks to General Assembly for hosting us and the Data Science ATL for making this happen. So what I'm going to be talking about tonight is just the general process of data science. How do we think about it? How do we approach a data science problem? And so I'm going to take you through a couple different approaches, two distinct approaches to looking at data science, different problems that we see in data science, and then go through kind of what questions we need to ask about those different problems, and then go through a couple examples of how we take what our approach is and actually implement it. So before we get there, Andy did a great job. I don't know where he went, but he did a great job of introducing pin drop. As he said, so we're a fraud company. We detect fraud, generate enterprise solutions for preventing phone-based fraud. So we put our solutions into call centers, and they listen to calls, detect the pops and clicks and artifacts in these calls, and can place where that call is coming from, what device that call is coming on. And we're able to say, hey, this isn't the person that's supposed to be calling from that. And detect fraud and prevent people's college funds from getting stolen, their retirement funds from getting stolen. So that's what we do. That's pin drop. Who am I? So I started my education in aerospace engineering at Iowa State University. Go Cyclones! They didn't do so well in March Madness this year. I think they broke a lot of brackets. Anyhow, I continued on from there to do my master's at Georgia Tech. In aerospace engineering, and then I got my MBA. So you might be thinking, okay, how did this guy get into data science? During my MBA, I started delving into the idea of data science for finance. So there's the link between the MBA and data science. And I did that. And my background, my aerospace background kind of helped me a lot with that. So I went from my aerospace background, was able to implement a lot of different data science techniques that we didn't actually call data science in aerospace engineering. And then I learned, oh, this is data science. So let's go explore this field, which is a very interesting career path. So that's a little bit about me. Let's go ahead and get into the talk. So we hear a lot of these phrases, big data, machine learning, data analytics. All of this is out there, these catchphrases, these hot topics. But what does it all mean? And this introduces like this whole field of data science that is kind of ambiguous. So a data scientist has a lot of tools in their toolbox. And a lot of people, statisticians, mathematicians, physicists, have these similar tools. Aerospace engineers, in my case, they have these tools. The question in data science and a lot of other fields is, how do we get started? An expert knows how to get started. A novice has a hard time getting started. So that's what I'm going to go through today. Is what are the right questions to ask? How do we get started? So let's take a look at two different types of a data science problem. One of which is where we have a data set. Okay, so we have some data that somebody's presented to us, whether it's just out of their own interest or we say, hey, this data set might be cool, and we don't know really how it could be useful yet. So how do we approach that kind of problem? A couple of examples of this are say the national electricity usage of the US, or parking ticket data in New York, or as in the pin drop case, cases of fraud at a calling card company. So we take a look at these different problems, and we have to ask the question, okay, how do we approach, we have the data already in front of us, but how do we actually explore that data? On the other side of this coin, there's a problem where we say, okay, we have a goal, we want to do something, but we don't really have data to support that goal. We don't have algorithms to support that goal. We don't know what is important there. So an example here, predicting tornadoes. That would be cool, right? determining stock market movement, or predicting March Madness. Okay, so these are more abstract tasks that we have that we don't really know, okay, what data is going to support this task. So we'll take a look at both of these examples in a little bit more detail later on in the presentation, and go through first the questions we want to ask for each of these different approaches to data science, and then go through examples. So first, let's take a look at the scenario where we have data, but we don't yet know how it's useful. So what questions do we need to ask there? So first, like, what information is available? What do we have in the data? So let's take a look at this New York parking ticket example. There was an article, I think it was an NPR article a couple months ago about this, that a data scientist in New York gathered parking ticket data from New York City and found that there was a crazy amount of parking tickets being ticketed to one fire hydrant. And I think it was something like on the order of $40,000 at that one spot over a year. So how did he come up with this? So, what kind of information is available to us? This, like, ticket location, the time of the ticket, the cost, potentially a couple other pieces of information. All right, so what can we gain from this? So the example I just gave, which fire hydrant produces the most tickets? That might be useful. Okay, so how about, are there any other data sources that might be available? So if we could gather like a vehicle identifier, like a license plate number or some anonymous identifier that's unique to the vehicle, the type of the vehicle, the color, then we can start asking more questions like, are specific colors of vehicles being targeted just because they stand out more? Or more expensive vehicles being targeted? Are there repeat offenders if people are being ticketed more often than others? So you can start to build out a case and start to understand this data. And then, of course, what techniques can we use? As a data scientist, we have a huge toolbox of techniques. And what should we use, right? So visualization, graphs, clustering, these are all ways of going through data and kind of understanding the structure of it. So let's take a look now at the other task where we have a goal in mind, but we don't yet have data and algorithms to support that goal. So using the example of trying to predict a tornado, what questions do we need to ask? So first of all, it's really good to understand the system, right? So for a tornado, what are the contributing factors? Is it weather? Well, of course, right? So is it high pressure, low pressure? Is it temperature? Is that involved? How about humidity? These sorts of things. And then we ask, okay, what should we predict? So should we predict the likelihood of a tornado? How about right now, or in an hour, or tomorrow, or in a week, right? All of these things have different connotations. So maybe it's very easy to predict a tornado in the next minute, but is that very useful? Probably not. Is it possible to predict a tornado that's going to happen tomorrow? Also probably not. So we need to reach a happy medium in what our task is for prediction. And then of course, when we know what data is available and what we want to predict, when we know what we want to predict and a little bit more about the system, then we need to figure out, okay, what data is available to allow us to make these predictions. So in the tornado example, again, NOAA data, satellite imagery, historical data, of course, to train on. These are all pieces of information that would be useful for us. So we have to brainstorm and think, okay, what data is going to be able to support these predictions? And then of course, we need to determine, okay, what techniques, what algorithms are we going to use? So, of course, the first kind of split in data science is, are we going to be going with classification or regression? And then you can go through a whole tree of classification algorithms based on your need, how complex the problem is, and then the same thing with regression on this other side. And then the question that is more of a feedback loop into the whole system is, how good are our predictions, right? So if we predict something that's not very good, then we know we have to go back and say, okay, do we really understand the system? Are we really predicting the right things? Do we really have data to support these prediction tasks, and so on and so forth? And then the key here in measuring your prediction is, and I'll use this example again with the tornadoes, is, if your measure of accuracy or quality of prediction is for a tornado, did we predict with high accuracy a tornado either not happening or happening at every minute of the year? I would get probably a 99.99% accuracy if I just said no, it's not going to happen, right? So that's not a very good metric. So you have to think and iterate on that. So you come up with good prediction metrics, so you can understand whether or not you're performing well. So with that, we've kind of introduced two separate data science ways of thought, right? So the first is we have a problem with data. We have the data, and we need to explore that data. We need to figure out how it's useful, if it's useful, what is the structure within. The second example is we have a goal in mind, and we need to figure out data and algorithms to support that goal. So we have those two. Let's take a look at an example of the first. Okay, so this is where we have data, and we want to explore and find structure in that data. So let's set the stage here. This is data that I've worked on at Pindrop. It's data from a calling card company, 2 months worth. So the information, and you'll notice I'm kind of going through the questions that I was outlining beforehand. So what kind of information do we have available in this data set? So we have a source caller, so that's a phone number, a destination phone number, the call, date and time, the length of the call, and then the type of fraud. Okay, so this calling card company was seeing fraud in their so essentially there are two types of fraud. One is call shop fraud, and the other is premium rate fraud. Call shop fraud is where somebody essentially steals a card and then sells that card to some unknowing end user. So they're using somebody's minutes, but they don't really know that they're using somebody's minutes. Premium rate fraud is where the fraudster is actually taking over the calling card company. So a lot of situations are where if anybody's used a calling card, they ask you to create a PIN, but everybody defaults their PIN to just the number that they're calling from. So if these guys get a number of somebody that uses that calling card company, then they can just call into the hotline and then use their minutes. So this is that kind of fraud. And typically they'd be calling a premium rate number that they own and then getting money that way. So they're not just doing it to do it, they're actually getting money out of it that way. So then we have to ask ourselves the question of, what information is contained in this? So the first approach is just to take a look at general statistics, like how much fraud is there? How many unique sources and destinations are there? And then we might want to say, okay, are there relationships between the source callers and the destination callers? Are people calling the same number frequently? Are there more sources than destinations, or vice versa? So let's take a look at some overall statistics from this data. So like I said, over 2 months, there are 50,000 records. Of those, there are about 2,700 unique sources and 13,000 unique destinations. So that's interesting. A lot more destinations than sources. The percentage of fraud is in total about 73%. Most of it is call shop fraud, so that's where people are stealing cards and then selling them to unknowing users. And then the lesser majority is the premium rate fraud, but you can see they're having a huge issue with this fraud. There's like 74% or 73% fraud in there. So that's a big problem in and of itself. And then only 27% genuine. So that's one reason why they wanted us to take a look. So we see, okay, lots of fraud happening, fairly few sources. Is there a relationship between these sources, between these source numbers? Are they similar numbers? So let's take a look at that. So how do we explore similarity between numbers? So I've got numbers up here. First one, 404-907-4485. Okay? The second number is extremely close to that number, but how do we quantify that, right? So it's one off in the last digit, whereas the third number is, again, it's two off in the last digit, one off in the second to last digit, and then one off in the fourth to last digit. Okay, so these are more different. The first and third are more different than the first and second. So I came up with a way to quantify that distance. And from that, we actually were able to take a look at a graph of these source ANIs. This is what it looks like. So that's kind of cool. Yeah. So what is this? Each point represents a single ANI. And ANI is yeah, thank you. And ANI is a phone number. So each point represents a single source phone number. And what we can see here is they're clumping, they're clustering. And what I'm clustering on, I'm telling the algorithm to cluster on how similar or different these phone numbers are. So based on our metric, that we came up with of, okay, the first two are pretty darn close and the first and third are further away, that metric generates this clustering. Pretty cool. Now we see some colors in here. I don't know if we can actually, you guys can see those, right? Yellow represents call shop fraud. Red represents premium rate fraud. And green, you can see green is kind of all around is genuine calls. So what we're seeing here is some pretty interesting behavior. Fraud is clustering with fraud. Who would have guessed? That's crazy. And I didn't know this when I was exploring this data. My task was simply to explore and figure out what was going on. So we see this, and then I say, okay, well, that's with source numbers. Does that happen the same with destination numbers? Indeed, it does. That's pretty cool, right? So what we see here is we've got a similarity metric between phone numbers. Just in the phone number, the structure of the phone number, we're seeing relationships between fraud and genuine. And even within fraud, it's separating the premium rate fraud and the call shop fraud. So you'll see yellow clusters with one another and then red clusters with one another as well. So that's a pretty cool result. How do we take advantage of this? So what I did was I took a look at creating features. This is another thing that data scientists use, a word they use a lot. Features to represent each of these clusters. So how big is the cluster? And how dense is the cluster? How much fraud exists in a cluster? And so on and so forth. And I use these features, and then I take a new phone number, and I say, what cluster do you belong in? And then based on that, I assign all of those features to, based on the cluster it belongs in, and give that to a machine learning algorithm. In this case, it was random forests. Good old scikit-learn random forests. Not too fancy, but that's all you need to generate a 95% true detection rate and a 0.5% false positive rate. So that's pretty cool. And this is temporally separated data. So we're taking a training set on phone numbers that came into the system previous to when we actually make this chart and check our true detection. So we train on data beforehand and then test on data after, because there's a time aspect to this problem. So this is the result, and for those of you who know what ROC curves are, it's the receiver operating curve, I think. Yep. this is what it looks like, and that's a pretty good one. So anyhow, let's take a look at what we just did. So a quick review of the questions that we wanted to ask ourselves. So what data is available to us? We have the source number, the destination number, the fraud type. What can we get from this information? So we can get an overall picture of what kind of fraud is happening, how often is it occurring. We noticed that lots of fraud is coming from the source numbers, from very few source numbers. So that leads us to think, okay, is there a relationship between these numbers? So then we develop a similarity metric, visualize this because it's always a good idea to visualize your data, and then color by fraud type, and lo and behold, there's some relationships in the data. Very cool. So then we always want to ask ourselves, okay, well, what additional information would be helpful? What would improve our true detection rate? Or what would improve the clustering and make it more effective in detecting fraud? So some questions we could ask. It's like, what providers are these numbers coming from? Are they like Google Voice or Skype callers that are always perpetrating this fraud? Does it occur on similar data sets? So we could take a look. We have one of the world's largest phony pot data sets at Pindrop, and we can take a look at that data. This is to describe that if you're familiar with email honeypots, it's essentially a trap for spammers, and they call, email into that honeypot, and then we know that that is spam. So it's a similar concept with phone numbers. So does this occur in similar data sets? So we can understand the extent to which this behavior occurs out in the real world. So those are the approaches to kind of take a look at a data set that you don't have information for, you don't really have a goal, but you just want to explore it. If we have any questions about that, I'm going to jump to a new example, so I'd be happy to field any questions. Yep. You first, and then you. Yep.
What was drawing the edges? Just the difference? Like where the
So the edges were connected based on the similarity metric. So if the similarity is beyond a certain threshold, there's no edge created. But if it's under a certain threshold, then there'll be an edge created. So you can think of like 0 to 1, 1 being the most similar and 0 being the least similar. And if I put the threshold at like 0.6 or something like that, then that happens. Yep.
How did the fraud type get set in the audio?
How did it get set?
Yeah. How do you determine?
So that was something that was handed to me. So the calling card company said these calls were fraud. They were premium rate fraud or call shop fraud.
So you have no idea what that was?
No, I don't. Yeah.
In your graph of the clusters, what was the x and the y axis on the picture?
They're meaningless. Yeah, it's just space. It's just a way to visualize the ANIs or the phone numbers.
And how does the space bound?
So that's using a graph clustering algorithm, and so network X is the actual module that I used in Python to do so. But it's just a gravity-based algorithm that takes things with edges and brings them closer together, and things without edges and spreads them away.
And it decided where to put them around.
Yeah. Yep.
What's the name of that software?
Network X. Yep. Cool. I'll take 2 more and then we'll move on. Yep.
It's one of the differences between the phone numbers worked out very well for you, but how do you happen to go down that alley quite a bit?
So actually, I did go down that alley right away, and I would have done a lot more analysis if I didn't go down that right away to explore different clustering algorithms or take a look at different aspects of the data. But it turned out, for this example, I actually did find that pretty upfront. I spent a good bit of time developing that similarity metric. to take a look at the phone numbers. There was one more question back there. Yep.
So there were only 50,000 records, for example. Have you ever had to work with data that doesn't fit in that would be something?
Yes, and I think, what is your question though?
So did you have data that was too big with memory on top?
So you can handle that in multiple ways. Yes, the question is, have you had data that doesn't fit into memory, and how do you handle it? So there are multiple ways of dealing with that. You can put it into a durable data store, and then only query what you need from that data store, so MySQL or Mongo or whatever. Or you can use a more efficient algorithm. So one thing that I did for this problem, because it actually takes too long to go through all of the nodes, is you come up with a sparse representation of the connections. And so that's another way to handle it. So you'll have a lot of zeros in this data, like no connections, and so you don't need to store all of those. So you'll go through and use a sparse representation of that data. All right, so let's move on. We're going to take a look at an example where we have a goal in mind. We want to predict March Madness, right? And we don't really know how to do it. We need to find the data. We need to go through all of these processes, figure out what algorithms we should use, ask the questions that we had highlighted. So if you guys don't know, March Madness is the men's NCAA basketball tournament that happens every year. It's happened since 1985 in the format of 64 teams. It's a single elimination tournament, and it is extremely hard to predict what's going to happen. There's always a contest. I think last year there was a $1 billion prize for a perfect bracket. Perfect bracket meaning you pick every single team right, who wins each game up until the finals. This is an extremely hard problem to do, and I was very interested to see what we could do with some data. So let's go into asking some of these questions. So what do we want to predict? So very generally, based on some team information that we have, we want to determine the result of each game. Okay, that's good. Let's figure out how to do that. So what do we know about this system, in this case, March Madness? So the tournament is played in a very structured, as I said, single elimination fashion, and there's a set of experts that will pick. There's 64 teams, and they'll pick the seedings all through. It's actually 1 through 64, and then teams 1, 2, 3, and 4 are all 1 seeds, and then 5, 6, 7, 8 are all 2 seeds, and so on and so forth. And they'll play in 4 regions. You'll see these 4 regions here, 1, 2, 3, and 4. And they'll play in a single elimination fashion, each moving forward if they win, and then there'll be 1 winner. So the committee picks 1 seeds. They're the best, supposedly, and 16 seeds, which are the worst, supposedly. Well, a 16 seed has never won the tournament, for sure. They've actually never beat a 1 seed, because a 16 seed is always paired up with a 1 seed at the beginning. So they give the advantage to the 1 seed. So there's some interesting structure in this tournament that enables us to make some predictions with confidence, right? So a 16 seed, 1 seed matchup, it's never happened, so let's predict it's not going to ever happen. Okay, sounds good. There are a ton of upsets. 25% of all games are upsets, which means a higher seed, like a 10 seed, beats a 5 seed. Okay, this happened with my alma mater. I don't remember who beat them. Was it UAB? UAB, I believe. I don't know who that is. But they beat Iowa State, and they were a 3 seed or a 4 seed. That was very frustrating. That busted my bracket. Anyhow, the other fact is nobody's ever picked the correct bracket. In recorded history, I'm sure there are people who claim to have done this, but ESPN tracks 11 million brackets a year. Yahoo tracks about the same amount, CBS, and in all of those, over the years that it's been tracked, nobody has ever picked a perfect bracket. And we can understand why with the combinatorial aspect of this. There are so many different options. So let's take a look at the results of 11 million users in ESPN. We can see here the chart is at the bottom. How many did they pick correctly? So what we can see is the best at the very tip out here is 50 games correct out of 63 total. That's okay, but most likely that was luck. This year, a 12-year-old won the brackets for ESPN. Somebody from, I think it was Lake Zurich, Illinois, won the brackets, and he ended up getting everything right but 7, which was amazing, but lucky. So we can see here that experts kind of do a little bit better than the general mass, but not much better. And you'll notice here, this spike is actually representative of the picking of just the seeds. So if you pick the whole bracket as a 1 seed beats a 16 seed, a 5 seed beats a 10 seed, always the lower seed beating the higher seed, you end up right about here. That's pretty good, so that might be my suggestion. Now, you'll see here, there's a little spike here. That's a pick for, about 10,000 clever people who picked all upsets. They didn't do very well. So you see, there's definitely information in the seeds. So the committee is doing a fairly good job, but they're not doing an amazing job because they're not getting everything right. So let's look at what we should try and predict. So there are a couple options here. One is we could pit each team against one another in a virtual way and try and predict the score difference between these teams. Or another option is to go ahead and just say, with this team as they are, just general information about how good that team is, how far are they going to get into the tournament? All right, so this means like a 0 is they lost in a play-in round, a 1 is they lost in the first round, and so on and so forth, 7 being they won the championship. So that would be a depth format. That's actually what I decided to go with because that's a little bit more amenable to a data science approach, but you can actually suss out the other one from the results of this. Okay, so what data is available for us? So we have a ton of historical team statistics. These are things like shooting percentage, offensive efficiency, defensive efficiency, so their strength of schedule, and so on. We have individual player statistics. We have historical tournament results. So this is the makings of a nice data science problem. So next we have to ask, what should we be doing as far as in our algorithm? So there are a bunch of different methods. We could choose classification. We could choose regression. For this, we're trying to predict depth. So depth we can consider more or less continuous and use a regression technique for that. The requirements for this are, one, we need to be able to capture the uncertainty of the problem. So there are a bunch of upsets that happen, and that represents uncertainty. So we need to find a method that can do that can represent this uncertainty. Okay, we're going to utilize continuous data. This is the information, the features that we have. So the shooting percentage, offensive efficiency, and so on, strength of schedule. And then we want to have timely results. I don't want to have to wait a year because I started doing this in a month before March, so I don't want to wait 2 months and then I'll say, hey, I got it all right, but the tournament's over. So we want something that is timely. So here are a couple options. Obviously, there are many, many more options than what I've listed here. Linear regression is always a good place to start. Might be a very simple system, and it might be able to represent our data well. So we take a look, and this is actually a chart here of some metric. It's called the Pythagorean metric. It's from 0 to 1. 0 on the left, and then 1 is on the x-axis here. 1 on the far right. And we can see this is depth. So this metric is actually doing pretty well. It says, generally speaking, when this metric is higher, closer to 1, we're getting champions. But there's a lot of noise in here, right? So the red line is linear regression for this metric alone, and it's unable to represent that nonlinearity. So we see kind of visually a curve happening here, and it's really unable to represent that nonlinearity. So let's not do that. Let's not use linear regression. So how about neural networks? This is something that can very, very natively represent nonlinearity in a system. So we could have something that draws a line like this, and that would be great, but it can't represent uncertainty. It can't represent those big variations in how well a team will do, those upsets. So let's move on to a more Bayesian technique. So Bayesian techniques allow us to represent that uncertainty. So the first thought, okay, let's go with a Gaussian process. Well, that's going to take a long time to run. Okay, why don't we use something like a Bayesian extreme learning machine? You may not have heard of that, but it is essentially the combination of a neural network, simple neural network, with Bayesian inference. And so this will allow us to both represent the uncertainty and represent the nonlinearity in the problem. So this is something that we'll go with and see how it works. So here's what the predictions look like for 2013. This is pretty interesting. The x-axis here is the depth from 0 to 7. So 0 to 7 here. And we can see that Louisville, who actually won the tournament in 2013, is way out in front of everybody else. They were, according to this method, was a clear winner. That's pretty cool, a pretty interesting result. And what we can see is these distributions are my confidence, my certainty about how well they're going to do. So the rest of the field, I really don't know. There's some distinction, but it's pretty clear that Louisville is going to win. So that's an interesting result, and I actually made 1 million brackets from this distribution, pulling samples from these distributions, and out of that I was able to get 51 correct out of 63 total. So if you remember, the best that anybody did, this was 2014, so it's slightly different, but it is on the order of the best that is seen in there. And this is out of 11 million. And I only used 1 million. So we can start to see that there's some value in this technique. So that's pretty cool. So let's take a look at what it looked like this year. So this was actually before the seeding occurred. So before the committee said, we declare Kentucky as the 1 seed and Wisconsin as a 1 seed. I think Duke was a 1 seed as well. I forget the 4th 1 seed. Anyhow, it was before that, and I just took a look at team statistics and said, all right, what does this look like? Interestingly, we have the 3 players here, 3 big players in the tournament right at the top. You can see Duke actually won the tournament, but Kentucky and Wisconsin were right there in the mix. So this was cool, and at this point in time, there was 9-to-1 odds, betting odds on Wisconsin winning the whole thing. So that's a pretty good bet. You bet $100 and get $900 back if Wisconsin wins. They were really close. They didn't win though. Anyhow, so how did we do in 2015? So using just those probability distributions, these distributions that we see here, to create a single bracket. Okay, so this is a single bracket, and utilizing them to understand what are the likelihoods of one team against another. So this is getting back to that first prediction task that we had, which was, can we pit one team against another team and see what the score difference is. Here it's the depth difference and how well they're going to do against one another. So what's the likelihood of one team beating another? Based on that information, you can create a single bracket, and of that you get 46 out of 63 correct. That's a 73% accuracy. That's pretty darn good. Now, if you take 1 million brackets, simulate that, you get 52 correct out of 63. And remember, the 12-year-old, he missed 8. Or no, 7. Sorry, 7. So we're approaching 12-year-old status here. And then simulating 10 million brackets, this is about what ESPN's bracket pool was. I think it was 11 million. We get 87% correct, or 87% accuracy. So that's a pretty interesting result, and this tells us that something's happening here where we're able to, with 1/10 the brackets, we're able to accomplish pretty much the best of the best in the top about 1% of all brackets on ESPN. So let's take a quick review of what just happened. Okay, so we asked the question, what do we know about the system? We know that it's very difficult to predict. We know that there's a lot of uncertainty in it, right? What should we predict? So based on the team stats, we want to either predict a score difference or how far they're going to go. And then we say, okay, what data do we have at our disposal? What can we use for this prediction? So we go with historical team statistics, player statistics, and so on. And of course, we need tournament results to verify and train our system. And then finally, we need to find the right technique. And this is an iterative process, something that you go through and say, okay, that didn't work really well, let's try this. Okay, that didn't work really well, let's try this. And so you continue along that path. In this case, I came up with, okay, we need a Bayesian technique to represent the uncertainty of the problem, and we need something that will be able to represent nonlinearity in it. So we combine the Bayesian with the neural network, the nonlinearity representation, with a Bayesian ELM, and move forward like that. And then, of course, you want to always ask the question of how can we improve this? So what additional data would be helpful? Would it be helpful to train on the entire season's worth of data? In this case, I only trained on tournament competition. Would it be helpful to have the level of experience of the teams, or perhaps where the teams are playing? Many different variations of this where you can explore that avenue and see, does it improve the system? So with that, I'd like to close up and thank you all for coming, and I'll be glad to take any questions you have. We? So what do we know about the system?
We, pin drop? Are you doing this within the context of pin drop, or who is we? Who is the group that's doing this research?
So this is me. We is me in this case. Yes.
I was curious, did you know a priori what factors go into the rankings of the tournament, and did you specifically choose features that were not redundant to those that fed into the ranking?
Yeah, interesting. So a lot of the rankings, it's by a committee. So a lot of the rankings are just expert opinion. And so what I did was I took a look at, it's actually Ken Pomeroy is a college basketball statistician. And he comes up with essentially a mathematical representation of teams' quality. And so I used a lot of data from his studies to power this study. Yeah.
So you said that Wisconsin had a 91 payout ratio.
Yeah.
What are the other 4 teams' ratios? If you bet on all 4, would you be mine?
So the question is, if everybody didn't hear it, what were the other payout ratios for the teams? I don't actually know. I think Duke was around a 4-to-1, but I haven't done the math to figure out if I would have come out on top. My guess is no, but that's always an interesting one.
Just picking the top 4.
Yeah, sure. Yes, in the back.
When you did your
resilience simulation, how did you end up deciding who won? The most frequent win I was finished in the place in the bracket?
Right. So the question is, once I did my simulation, how did I decide who won? So the bracket is very structured. So you just follow that structure, and each team has a predicted depth. And if the depth of one team is further along than the depth of another team, they win that game and move on. And so in that manner, you can play out the whole tournament and understand the final depth of each of the teams. Yeah.
Do you know what the accuracy is of the sort of, what I would think of as the null hypothesis model, which is pick according to seeds?
Yeah, so it's about 60%.
Okay, so
or,
this
or
does
thereabouts.
improve over the sort of stupidest idea you have.
Yeah, fortunately. That is a very good approach, though. When you're looking at a problem, you always want to make sure, like the tornado example I gave earlier, of just predicting no tornadoes all year long, you'd be 99% accurate, right? 99 point, a couple nines, right? Accurate. So always a good approach. All the way in back.
For your figure that you had by year, your annual distribution, what was the y-axis?
I'm not sure which one you're referring to. This one? Okay, so the this is a histogram, essentially. So the y-axis is frequency. Yeah?
Going back to your calling fraud example, you could send information about, pretty much you get a call detail record, CGRs, destination, termination, and duration. So, what else do you add to it in order when you talk to a calling fraud agency or call centers? There's mention about sound or clicks in the background. How do you tie that data to so it creates value to the source or the company?
Sure. So those are actually, the question is how do I integrate the call detail record, the data that I had in this example with the artifacts in the background noise of a call. Those are actually two separate problems. Most of the clients that we serve, our product is on site, and we'll be gathering the information, the audio data on site. So that information is used in a completely separate prediction engine than what I presented here. Does that answer your question?
Yeah, I'm kind of curious. You mentioned, or when Andy mentioned about the presentation about what the company does. Kind of curious to see how you tie the information and how it creates value to the call centers or the credit card company or calling card company.
Right. So of course, in this scenario, if you're able to detect the fraud simply by the phone number, when a new phone number comes in, I can make a prediction to say, this is likely fraud. And so that benefits them because the calling card company has to foot the bill for all of that. In the back? Yep.
So it's interesting that you brought up on the two sides of the coin at the beginning. You brought up weather prediction on the other side of the coin. And if we've been having this conversation 30 years ago, everyone in the audience was talking about making models. And that's the one word that you have mentioned tonight is modeling. Because there are there's well-established equations for modeling fluid dynamics and explosive equations. And for predictive modeling using equations is the sort of important aspect of prediction. And so 30 years ago, no one would have been talking about data and features in this way, which is a very cool thing that's been changing in the last few years. But I guess my question is, because I see this a lot in data science right now, is the lack of discussion of our hypothesis and model. Because I think that still has an important role. My question is, have you been considering a way to represent a hypothesis or model as part of doing this in order to maybe get a little bit more out of it?
Yeah. Very interesting. So a lot of my experience from aerospace is in modeling, and creating physics-based models, as you mentioned, with weather, the fluid dynamics, and everything. So there is definitely a synthesis between those two, and that's very valuable. One thing that you get kind of for free with data science and these machine learning techniques is you don't actually have to understand the underlying system. That is a critical part of creating a good data science model, machine learning model, is understanding that system. But a lot of people are able to get away with it without creating those models. Sure.
I think you get away with, say, 95% or something like that for receiver operator characteristic. It's really good, that's great. But if you want to go beyond that, then you might start to delve into the actual model to help you.
Yeah, and very, very good. And there's always a trade-off, right? So there's a trade-off in cost and time to a solution in that. So appreciate that comment. Yeah.
Kind of follow on that, as a data scientist, how much do you treat to a certain gut feeling or intuition about the process or what you might apply to a problem? For instance, what led you to figure that the kind of distance of similarity or number was what we meant to be?
Sure. So in that example, I thought, well, there are very few source numbers, right, as compared to destination numbers. So perhaps there's a relationship between them. And my first instinct is, okay, how can I represent a relationship between phone numbers? I look at the numbers and I say, okay, maybe there's a similarity between these in the number. So you've got a caller from New York, the same area code, and perhaps it's a corporation or a fraudster that's bought a block of numbers. And so with that knowledge, I say perhaps this block of numbers that would indeed be similar to one another are exhibiting what I've shown, which is clustering of fraud based on those similarities. So it's a little bit of a mixture of I know a little bit about the problem and I'm just trying stuff, just interested to see what happens.
In that problem, all we had was a number, a label. So all he can do is just play with numbers. So if you cannot put a metric on the numbers, that's the only information he has. So that's the first thing you try.
So you find that just doing a lot of this over time gives you
Yeah.
Intuition.
Yeah.
Like this looks like a Bayesian problem.
like Bayesian analysis.
Right. So as you, just like you're saying, as you do this a lot, you start to understand, like, oh, okay, I need uncertainty, okay, we might go in the Bayesian route here. Maybe I can get away with it without doing it, so let's try it this way first. But then you're going to fall back on it if it's unsuccessful. All right, one more question. Yeah.
Can you speak to the process of putting predictive models into deployment and how that influences what methods you choose from the beginning? Like if you need real-time deployment as opposed to looking at something after the fact?
Yeah. So that's a huge consideration, especially in the work that we do. Is this algorithm going to take up way too much memory? Or is this algorithm going to be way too slow to query, right? So we've trained the model. Maybe we can handle training this algorithm over, 3 days, and then hold that model and say, all right, let's use this now, and then come up with a training policy to retrain models as we get new data. But definitely, that's something that you always have to consider. And you kind of, as you get with bigger and bigger data, the algorithms that you have available to you get smaller and smaller to be feasible to actually compute for a real-time system or even something that you have to analyze after the fact. All right, I think we've hit our time. Appreciate it, everybody. Thank you.